Dear all, in this video we will go over power series and combination and addition of power series. So in differential equations for series solutions, we can use power series to solve differential equations. Although in this course we're not going to go over convergence tests, we are assuming that the ones we're going to use are already convergent series. Because in order to solve the differential equations, we need the series to be convergent. On the other hand, as you can notice, the power series is defined as y equals to sigma n from 0 to infinity, a of n, a sub n, x minus x0, x sub 0, n to the power n. So this x sub 0 is basically where our series is centered around. And if we look at Maclaurin series, where it's centered around 0 for Taylor series, the idea is pretty similar in this course as well. Until we meet singular points and the singular points of a series, we're gonna assume that the x0 is already centered around 0. Most of the time this will be already given to you in the questions. So we're gonna find the series solutions centered around x0 equals to 0. And that's gonna make our lives a little bit easier, but in the future we're gonna use Fabini's method to solve differential equations which are centered around a singular point, and that's going to be another important topic. So now let's see how the power series centered around x equals 0 looks like. So for power series centered around x0, our notation will be the same, n equals to 0 to infinity, a sub n, x to the n power. Because our x0 is considered to be 0, our first derivative will be followed n equals to 1 to infinity, a sub n times x to the n minus 1, and the second derivative will be y double prime equals to sigma n equals to 2 to infinity, a sub n times n minus 1 to the x to the n minus 2 power. So basically, the inside of derivative of a summation will be the same as you'll know from your calculus courses, taking a derivative of a variable with the constant in front of it. However, the series will have different indexes as you increase the number of derivatives, and the index increases proportional to the amount of derivative you're increasing. So if we get the first derivative, our summation will start from 0. And there is a very nice proof behind it, there's a nice explanation behind it, but we're not going to go too deep into the reason why. What we now will do is solve some problems on this series. Now let's combine these series into a single power series. Well, when we're solving differential equations using series, we don't want a bunch of series being lined up because this makes our work almost impossible to work with. So we want to combine these series into a single power series so that we can build off of our solution based on what we have there. So in this problem, what we want to do first is all of these times when we want to combine series, we're always going to check the exponents first. Are the exponents equal? If we have equal exponents, then the next thing we want to be checking is what about the indexes. And both when the indexes and the exponents match, we are able to combine these series into a whole big chunk of series. So now the first thing I want to tell you guys is we're going to write this down and notice how the exponents are different. The first one is x to the n power, the second one is x to the n plus 1, the third one is x to the n minus 2. So these are not good, okay? And there are really nice tricks we can use to make all of them the same equal x power, okay? So first of all, we must decide what our base should be, and I think x to the n would be looking really good. So I'm gonna leave this first series as it is, n equals to 1 to infinity, x to the n power over n, plus. Now we have the second series, right? Well, notice this. There's a really nice trick where we can get rid of the n plus 1 power in this series without doing an expansion of this series. And that is basically substituting for n. Well, you might see this very commonly where n is defined as a k plus 1 or a k minus 1. to make everything much more easier. But in this course, we're not going to do that method because I believe it's really complicated, because it's just the same thing what we're going to do. We're going to do it much easier and simpler. Okay, so over here, just notice this. You want to subtract 1 from the exponent, right? We have an n plus 1. We want that to be n. So if we're going to subtract 1, we're going to do the opposite operation for the index. So we're going to add 1. So our series will be n plus 1 to infinity of x to the n divided by the series. Now we're going to have to subtract, because every time we see n, we're going to substitute what? N minus 1 factorial. And this is actually basic algebra. The other method is actually the same thing. It comes from the same place. We're going to substitute a k variable and do all of this work. But when you can actually save a lot of time just doing this. Okay? And likewise, we also want to do the same thing. We want to add 2 for the exponent. So we're going to subtract 2 from the index. Okay? We're going to subtract 2. And subtracting 2 will give us n equals to 0, which is actually quite nice to work with, and you will see the reason very soon. So we're going to add n plus 2, and we're going to substitute n plus 2 everywhere we see n. So we're going to start with n plus 2 to the x to the n power. Now that we have our x to the n power, it's pretty good. And n plus 2 factorial. And notice this. I hope you guys can notice this, because we should already know this, that here we have a important series. We have n plus 2 divided by n plus 2 factorial. And what can we do with these factorials, guys? Well, n plus 2 factorial is just n plus 2 times n plus 1 times n minus 1 times n minus 2. We'll keep going until n is vanished. So the top we have it multiplied with n plus 2. We multiply n plus 2 times x to the n. So those n plus 2's should cancel each other out. And, why not just simplify things when you can, right? So we're going to rewrite this series as the series from n equals 0 to infinity of x to the n over n plus 1 factorial. Okay? N plus 1 factorial. And now, notice how our series are quite similar. In the first term, we have x to the n power. The second term is x to the n. And the third term is also x to the n. Now, if we check the indexes, our indexes will be n equals 1, n equals 1, and n equals 0. So the only problem is with the third series, because we have a different index. So what we can do is, well, it's the first thing that comes to mind. Let's just expand the first term, the n equals 0 term, add that, and then combine everything. So we're going to have a little addition operation between the two series. So what we want to do is just expand the first term. So plug n equals 0. Okay, let's plug n equals 0. So if we plug n equals 0, x to the 0 is going to be 1, divided by 0 plus 1 factorial, which is 1 factorial. So we're going to have just plus 1. So 1 plus, and I'm going to rewrite this series. Okay, n equals 1 to infinity, x to the n over n plus n from 1 to infinity, x to the n over n minus 1 factorial plus, now our index will change for this final piece of the series. We're going to have an n equals 1 of this series. So our series will look like n equals 1 to infinity of x to the n over n plus 1 factorial. And now our job is really simple. We're going to write whatever series, whatever sigma notation we have. Okay, let's start with that. 1 plus, and our sigma will be at sigma n equals 1 to infinity. Okay, and now imagine we do this. Okay, we're just going to do some algebra here. Imagine you factor out an x to the n power from everything when we're adding it, right? We're just doing an addition, guys. Don't overcomplicate this. We're just adding x to the n over n plus x to the n over n minus 1 factorial plus x to the n n plus 1 factorial. Okay, so we're just going to add these together. So we're just going to act like we're making a factorization. So we're going to have 1 over n plus 1 over n minus 1 factorial plus 1 over n plus 1 factorial. Okay, and at this point we can just leave it like this,